At 14:36 Universal Time on July 20th, a sunspot that did not exist on Friday fired a moderate solar flare toward this planet. It was the region's second eruption in hours. It outran the official forecast by an entire flare class, and it came from a machine the Sun assembled in full view of our telescopes in under 2 days. The measurements say the energy for something far larger is already stored inside it. The only thing holding that energy back is a cage made of the region's own magnetic field at the exact spot on the Sun that faces Earth, and its load is still growing while a separate river of fast solar wind, forecast days ago, arrives within 48 hours. So this week comes down to one question. How long does the cage hold? If you want that question tracked with clear eyes instead of hype, subscribe to the Sky Lab and tap the like button. Then drop a comment with where you're watching from and whether you've ever seen the Aurora yourself, because by Wednesday night some of you might. Now, let's get into it. Part 1. The morning the Sun looked quiet. On the morning of July 20th, 2026, the official word on the Sun was simple: quiet. The strongest flare of the previous day had been a C2.1, a minor flicker that most instruments barely registered, and no one on Earth would ever feel. Government forecasters at the Space Weather Prediction Center rated the chance of anything in the M-class, the moderate class, as slight. X-class flares, the big ones, were not expected at all. One report published that morning described 3 numbered sunspot regions on the Earth-facing side of our star, all of them, in its words, largely inactive. The Sun, by every official measure, was dozing. That report contained one sentence that mattered more than all the others. Tucked into the region-by-region rundown was a note that forecasters were watching a new, unnumbered region in the east, a patch of magnetism that had not existed a couple of days earlier. The note said only that it showed continued growth. By 14:36 Universal Time that same afternoon, that new region had a number, a location almost dead center on the solar disk, and a confirmed M2.5 solar flare to its name, 25 times more powerful than the strongest event of the previous day, strong enough to push a minor radio blackout across the sunlit side of our planet. The forecast that gave M-class flares only a slight chance had been outrun in a matter of hours, not by an old familiar sunspot finally losing its temper, by something brand new, something that assembled itself while we watched. The region is called Active Region 4493, and the reason this video exists is not just that it flared. Moderate flares happen all the time. The reason is what observers watched it do in the 48 hours before it flared, and what the measurements say it is still doing right now. Because the data shows a sunspot complex that went from literal non-existence to a multi-cored, magnetically twisted, eruption-capable machine in less than 2 days, growing at a pace that seasoned solar watchers called some of the most impressive of the year, in almost the exact spot on the Sun that faces Earth. The measurements say the energy for a top-tier flare, an X-class flare, is already sitting inside it. The only thing holding that energy in place is a cage made of the region's own magnetic field, and here is the part that turns this from a curiosity into a story you need to hear to the end. That cage is being tested while another solar event, one that was already on the calendar, bears down on us. 2 days ago, a giant hole in the Sun's atmosphere finished rotating into position, crossed the center of the solar disk, and aimed its fire hose of fast solar wind straight at Earth. That wind is on its way right now. Government forecasters expect it to arrive late on July 21st, with minor geomagnetic storm conditions likely on July 22nd. The planetary K-index, the number that measures how hard Earth's magnetic field is being shaken, is forecast to reach 5, the storm threshold. So hold both of those facts in your head at once, because the entire story lives in the space between them. A stream of solar wind we have known about for days is about to sweep across this planet. And immediately beside the hole that produced it, close enough to matter, the Sun has spent the last 2 days building something new. Something that has already started erupting. Something no agency on this planet predicted, because it could not be predicted, because 48 hours ago there was nothing there to predict. That is the machine we're going to take apart tonight, piece by piece. And it genuinely is a machine, in every sense that matters. It has a power source, magnetic energy hauled up from the interior of a star. It has moving parts, spots of opposite polarity grinding against each other, one of them literally rotating in place like a gear. It has a housing that contains the whole assembly, the magnetic cage, and it has a trigger nobody can see, which is exactly why nobody can tell you when it fires. To understand why researchers watch a region like this so closely, you have to understand what an M2.5 actually is. Solar flares are ranked on a letter scale A, B, C, M, and X, and each letter step is 10 times stronger than the one before it. Within each letter, the numbers scale it further, so the jump from that morning C2.1 to the afternoon M2.5 was not an incremental uptick, it was a leap of more than an order of magnitude in peak X-ray output. In the time it takes you to read this sentence, a flare like that releases more energy than every power plant on Earth could generate in years. When it happened, X-rays travelling at the speed of a light crossed 93 million miles in 8 minutes and slammed into the top of our atmosphere, tearing electrons off atoms across the entire day side of the planet and thickening the electrically charged layer that radio signals have to punch through. Aviators and operators using certain high-frequency radio bands on the sunlit side of Earth felt that flare as static and fade-outs. That is a minor blackout, the R1 level. It recovered within the hour. For a sense of where an M2.5 sits in the sun's repertoire, the scale runs from a class events, thousands of times weaker, up through B and C, the background crackle of an active star, into M, the moderate tier that begins touching Earth's radio environment, and finally X, the class with no ceiling, where the numbering simply keeps counting upward. The most powerful flare of the modern instrumented era, in November 2003, was estimated around X45, and it saturated the sensors built to measure it. Monday's event, in other words, sits far down the ladder of what this star can do. That is worth holding on to in both directions. It is why nobody serious is calling the flare itself dangerous, and it is why the real question of this video is not the rung, but the climbing. The flare itself, in other words, was not the headline. Earth shrugs off M-class flares routinely. The headline is the machine that made it, on its first day of operation. The headline is the production rate. Consider what the observing community actually logged over those hours. First, small C-class flares began popping off, not from one spot within the new region, but from several distinct locations inside it, a sign that multiple separate magnetic engines were spinning up simultaneously inside a single sunspot group. Then came an M2. Then, at 1436 Universal Time, the M2.5. Each eruption traced back to the same neighbourhood near the centre of the region, a place where, as we will see, the magnetic field has folded itself into the single most dangerous configuration a sunspot can wear. After the M2.5, the X-ray flux from the sun relaxed back down to roughly the C1 level, like an engine settling back to idle. The proton monitors that watch for radiation storms stayed quiet below every alert threshold, and the coronagraphs, the instruments that watch for eruptions of solar material, found no Earth-directed cloud of plasma connected to the flare. Nothing thrown at us, not yet. The flare had been what physicists call impulsive, a short, sharp spike of energy rather than a long, sustained release, and impulsive flares, as a rule, are the kind that stay on the sun. That detail, the shape of the flare in time, turns out to be one of the most important clues in this entire story, and it points directly at the cage. All of that, every number in it, is current as of the recording of this video. I want to be careful with you about that, because this region is changing measurably hour by hour, faster than daily bulletins can keep up with, and honestly faster than videos can. By the time you hear this, the flare counts may be higher. The classification may have been upgraded. That is not a reason to wait for better information. That is the information. The speed is the story. Because something built this fast, this complex, this close to the centre of the Earth-facing disk, is vanishingly rare, and it forces a question that sounds simple and is not. If the sun can construct an eruption-capable machine in 2 days, in full view of our best instruments, without a single forecast seeing it coming, then what exactly is our warning system for? What did we think we would see first? The answer to how this thing was built in 48 hours starts far below anything our telescopes can see, in a place where a star keeps its secrets. Part 2, 48 hours from nothing. Picture the sun as it looked on Friday, July 17th. If you had pulled up the live imagery that most solar watchers check every morning, the visible disk would have shown you a handful of modest sunspot groups, dark freckles scattered across a glowing surface, none of them doing much of anything. The patch of solar surface just north of the equator and east of the central meridian, the region we now call 4493, was blank, not quiet. Blank. Unmarked photosphere. The same featureless granulated surface that covers most of the star on most days. There was nothing there to name, nothing to photograph, nothing to fear. By Saturday, magnetograms, the specialized maps that show magnetic fields on the solar surface, began registering something coming up underneath that blank patch. Concentrations of magnetic flux, north and south polarity, surfacing side by side and spreading apart. By Sunday, the region had visible spots, and then, over roughly 18 hours spanning Sunday into Monday, the process went from steady to explosive. Watchers who track these magnetograms daily described strong mixed magnetic flux pouring through the surface, new field emerging faster than the region could organize it, with the growth concentrated so intensely on one half of the group that frame-by-frame animations of it look less like weather and more like time-lapse footage of a construction site. Keep the timeline in your hands, because the timeline is the anomaly. A sunspot that did not exist on Friday was, by Monday afternoon, firing off the strongest flare the sun had produced in days. Nothing about the individual ingredients here is unheard of. It is the speed of assembly, and where it happened, that pushed the observing community from interested to riveted. To put hard numbers on the growth itself, the region went from unlisted to carrying multiple spot cores in roughly a day, and its spot count and total area was still climbing at every observation as of recording time. Sunspot area is measured in millionths of the visible solar hemisphere, and for scale, the mature giants this channel covered around Independence Day sprawled across more than 1,400 millionths, roughly 7 times the surface area of Earth. 4493 is nowhere near that size yet. What has analysts' attention is not its area, but its slope, the rate of change, because in every reconstruction of history's fast-emerging monsters, the slope was the earliest number that looked wrong. Sunspot groups are born, live and die on a spectrum of timescales. Small ones bubble up and dissolve within hours or days, and the sun produces those constantly, the way an ocean produces whitecaps. Large, complex groups, the kind that make headlines, typically take shape over many days, or arrive at the Earth-facing side already built, having done their growing on the far side of the sun where we cannot watch. What almost never happens is this: a major complex assembling itself from bare surface, at full speed, in the middle of the visible disk, with the entire planet's instrumentation pointed at it. One long-time observer, watching the growth animation, put it plainly, some of the most impressive developments seen all year, unfolding not at the edge of the sun where detail is smeared by perspective, but nearly face-on, in the one location where we could see everything. That location deserves a moment of your attention, because it is doing 2 different kinds of work in this story. The region sits near 5 degrees north of the solar equator, about 13 degrees east of the center line of the disk. In practical terms, that is close to dead center from Earth's point of view, and disk center, in space weather, is the loaded position. The sun rotates once every 27 days or so as seen from Earth, carrying its spots across the disk from east to west like riders on a carousel. A region near the eastern limb points its eruptions off to the side of Earth's position. A region near the western limb has begun aiming away toward the far side of our orbit. A region at or near disk center is pointed at us. Whatever it throws in our general direction. 4493 surfaced almost exactly there, and because it emerged east of center, the sun's rotation is currently carrying it through the aimed-at-Earth zone, a crossing that will take roughly the next several days. The machine did not just build itself fast, it built itself on the one stage where everything it does for the next week happens facing the audience. Now, is that placement meaningful? No. This is worth saying clearly because your pattern-seeking brain, and mine, wants it to be meaningful. Sunspots emerge where the underlying magnetic field happens to surface. The sun does not know Earth exists. Regions come up at disk center at random, the same way lightning occasionally strikes the one tree in an empty field. But randomness cuts both ways. Unlikely placements are not impossible placements, and when one lands, the consequences are real regardless of the odds. The consequence of this one is that a newborn, rapidly intensifying magnetic complex will spend its adolescence, statistically the most eruptive phase of a sunspot group's life, staring straight down the barrel at us. That fact does not require any cosmic intent to matter. Geometry does not care why it happened. There is one more thing the timing gave us, and researchers know it. It gave us the show of the year. A scientist who studies how sunspots form could spend an entire career working from statistical catalogues and lucky partial observations, because the birth of a major active region in plain view, at high resolution from start to finish, is a rare gift. The Solar Dynamics Observatory, the spacecraft that photographs the Sun continuously in multiple wavelengths, captured every hour of this construction, every surge of emerging flux, every spot merger, every twist. Whatever else 4493 becomes, it is already one of the best documented sunspot births in the modern observing era. The frustrating irony, and the theme this video keeps returning to, is that watching something being built in perfect detail is not the same as being able to do anything about it. We have the full construction footage of a machine we cannot switch off, and the construction footage shows the machine still growing. As of the most recent analyses available at recording time, the flux emergence has not stopped. Estimates suggest it may have eased slightly, but observers describe the slowdown as barely noticeable. New magnetic field is still arriving at the surface. New spots are still darkening. The complexity, and this is the crucial part, is still increasing, which means every hour that passes the amount of stored magnetic energy inside this region goes up, not down. Think about what that means for everything you heard in the first part of this video. The M2.5 was not the machine at full power, it was the machine during assembly. It flared before it was finished. Which brings us to the question this entire part has been building toward, the one that separates casual viewers from people who genuinely understand what they are looking at. Where does a sunspot actually come from? What is physically rising out of the sun when observers say flux is emerging? Why can a star go from blank surface to eruption engine in 18 hours? And why can no forecaster on Earth, with billions of dollars of instrumentation, see it coming even a day ahead? The answer lives roughly 140,000 miles beneath the solar surface, in a layer of the sun that no telescope has ever seen, and no telescope ever will. What happens down there stayed hidden for most of the history of astronomy. What we now know about it explains almost everything you watched happen this weekend, including why the weekend itself was the first warning anyone could possibly have gotten. Part 3. The machinery under the surface. Every sunspot you have ever seen a photograph of began its existence as a buried cable of magnetism, coiled somewhere in the interior of the sun, invisible to every instrument humanity owns. That is not a poetic flourish. It is the literal physics, and it is the reason the events of this weekend could not have been forecast by anyone, anywhere, at any price. Here is how the machine works. The sun is not a solid object. It is a ball of plasma, gas so hot that its atoms have been stripped into charged particles, and charged particles in motion generate magnetic fields. The interior of the sun rotates unevenly. The equator laps the poles, completing a rotation in roughly 25 days, while the polar regions take more than 30. Deeper still, the radiative core rotates almost like a rigid body, while the churning envelope above slides over it. At the boundary between those two zones, a thin layer of shear that scientists call the tachocline, the sun's large-scale magnetic field gets stretched, wound, and amplified like thread on a spindle. Year after year, that winding builds ropes of concentrated magnetic field, thousands of times stronger than anything at the visible surface, stored roughly 140,000 miles down. A magnetic field has a physical property that turns out to run this entire story. It exerts pressure. A tube of plasma threaded with a strong magnetic field pushes outward against its surroundings, which means the plasma inside the tube can be thinner, less dense than the plasma around it. And in a star, less dense means buoyant. The same principle that lifts a beach ball from the bottom of a swimming pool acts on a magnetic flux rope in the solar interior. Once a section of that buried rope becomes buoyant enough, it begins to rise, arching upward through more than 100,000 miles of churning plasma, and nothing in the sun can put it back. That rise takes weeks to months through the bulk of the interior. But the final ascent, through the last few tens of thousands of miles accelerates dramatically, and the actual breakout, the moment the top of the arch punches through the visible surface, can go from undetectable to unmistakable in hours. When the crown of the arch breaches the photosphere, we see it as two clusters of magnetism of opposite polarity, the two legs of the arch surfacing side by side. Where the field is strongest, it chokes off the rising currents of hot plasma that normally deliver heat to the surface, and those patches, starved of heat, cool by thousands of degrees and darken against the brilliant background. That darkness is a sunspot. A sunspot is not a thing on the sun. It is the visible footprint of a magnetic structure, most of which remains below, a mountain range seen only by its peaks. The numbers involved are worth pausing on because they set the scale of everything else in this story. The undisturbed solar surface runs at roughly 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. The dark core of a sunspot, the umbra, where the magnetic field is strongest, is refrigerated by that field down to roughly 6,500 degrees Fahrenheit. Cooler by a third, which is the entire reason it looks black. It is not black. An umbra torn free of the sun and hung alone in the night sky would glow orange, brighter than the full moon. It only appears dark because everything around it burns hotter. The field strength inside an umbra reaches several thousand Gauss, thousands of times the strength of Earth's magnetic field at the surface, strong enough to physically strangle the boiling convection that everywhere else delivers heat from below. And the spots themselves are not small. Ordinary spots are the size of continents. The cores of a large group like the one that surfaced this weekend can swallow the Earth whole, with room to spare. When we say a machine was built in 2 days, we mean a machine with Earth-sized moving parts. It is also worth remembering how recently any of this was knowable at all. Humans have recorded dark marks on the sun for at least 2,000 years. Chinese court astronomers logged them through haze and sunset long before telescopes, and Galileo and his contemporaries tracked them in the 1600s, well enough to prove the sun rotates. But for nearly all of that history, nobody knew what a spot was. The discovery that sunspots are magnets came only in 1908, when George Ellery Hale, at the Mount Wilson Observatory in California, spread sunspot light into its component wavelengths and found the telltale splitting of spectral lines that only a strong magnetic field can produce. One measurement, and the sun stopped being a lamp and became a machine. Every word of this video descends from that afternoon. Now connect that to what observers watched this weekend. The blank patch on Friday was blank because the rope was still below the surface, and there is no instrument on Earth or in space that can directly image a magnetic flux rope beneath the photosphere. The eruption of activity on Sunday and Monday, the strong mixed flux that watchers described pouring through the surface, was the breach itself, the arch, or more likely a tangled braid of multiple arches arriving from below. Everything about the violence of the arrival was telling us something about the structure that had been hidden. A simple, orderly flux rope surfaces as a simple, orderly pair of spots. What surfaced here came up fast, fragmented and mixed, positive and negative polarity interleaved at close quarters, new flux still arriving hour after hour. The machine was not assembled on the surface. It was assembled in the dark, over months, somewhere below, and what we watched this weekend was only the delivery. That is the honest answer to the question everyone asks after a weekend like this one. Why was there no warning? Not because agencies were asleep, and not because anything was concealed. The warning did not exist to be given. Our forecasting of solar activity is, in a precise sense, weather reporting for a surface. We can see spots once they form, measure their fields once they surface, and estimate probabilities of flares from regions that already exist. What we cannot do, at all, is see the ropes before they arrive, heliosismology, the technique of reading sound waves that pass through the sun the way earthquake waves pass through Earth, can detect the largest active regions on the far side of the sun, and in research settings it has occasionally caught the acoustic signature of a large flux rope in the final hours before emergence. Hours, single digits. For a rope already almost at the surface, there is no version of the science, current or on any horizon, that gives days of notice for new flux. The interior of our star is, for practical purposes, opaque until the moment it is not. Sit with the asymmetry of that for a moment, because it is the core tension of this entire video. Humanity operates a fleet of spacecraft staring at the sun without blinking. We photograph it in a dozen wavelengths, map its surface magnetism every 45 seconds, and sample the wind blowing off it from a station 1,000,000 miles upstream of Earth. It is one of the most closely watched objects in all of human activity, and a structure carrying the stored energy of billions of nuclear arsenals rose through the last 100,000 miles of it, surfaced, organized, and began erupting, on a weekend, with our warning time amounting to essentially the time it took to look at the new pictures. Total surveillance, zero control, and almost zero anticipation. What we cannot see, we cannot predict. What we cannot predict, we certainly cannot stop. There is one more lesson in the physics, and it is the one that should genuinely change how you watch the next few days of this story. The violence of an active region is not set by its size alone. It is set by how the emerging magnetism is arranged, by how much twist and shear and stored stress the rising structure carries with it from below. Most emerging flux arrives reasonably tidy, relaxes into a simple pair of spots, drifts apart, and dies quietly without ever producing a significant flare. The dangerous regions are the ones that arrive wrong, tangled, compressed, twisted around their own axis, carrying stress they cannot easily shed, with opposite polarities forced against each other instead of politely separating. So the question that decides whether this weekend was a curiosity or the opening chapter of something larger is simple to state. When the magnetism of region 4493 came up through the surface, how did it arrive? Tidy or wrong? The magnetograms have already answered that question, and the answer is the reason experienced solar observers, people who have watched thousands of regions come and go without losing a minute of sleep, spent Monday glued to their screens. Part 4. An engine built wrong. The magnetograms of region 4493 show a structure that violates the Sun's own rulebook, and to appreciate how unusual that is, you first need to know that the Sun has a rulebook at all. Sunspots obey laws, not suggestions, laws, patterns so consistent that they have held across every solar cycle since systematic observation began. The first is Hale's polarity law, named for the same George Ellery Hale, whose Mount Wilson measurement turned sunspots into magnets, and his was, incidentally, the first detection of a magnetic field anywhere beyond Earth. Hale's law says that sunspot pairs in a given hemisphere line up with the same polarity leading the way, and the arrangement flips between the northern and southern hemispheres, and the whole pattern reverses with each 11-year cycle. The second is Joy's law, which says the axis of a sunspot pair is not perfectly parallel to the equator, but tilted, slightly and predictably, with the leading spot a little closer to the equator than the trailing spot. These laws are not cosmic bureaucracy. They are the surface fingerprint of that great buried winding process we just walked through, the visible proof that spots are the tops of arches rooted in an organized global field. The tilt in particular is no decoration. Joy's law tilt is believed to be the twisting work of the Sun's rotation acting on each rising arch, the same force that curves hurricanes on Earth nudging every emerging loop into its slight regulation lean, and that lean is a working part in the Sun's own 11-year engine, feeding the slow conversion of each cycle's field into the seed of the next. When a region follows the laws, it is telling you it came from orderly machinery, and it is doing its small assigned job in the star's long project. 90-something% of regions follow the laws. Region 4493 does not. Its main polarities are arranged roughly north to south, rotated away from the east-west axis the rulebook demands, in a configuration observers have described with a term worth remembering, anti-joy. A tilt not merely imperfect but contrary. Watchers with years of daily observation said openly that they struggled to recall a recent region that arrived with this kind of orientation, and that matters for a reason far more concrete than rarity for its own sake. A region that emerges against the statistical grain is a region whose buried rope came up twisted, sheared, or deformed, carrying disorder from below. Tilt is not cosmetic. Tilt controls how the region's opposite polarities meet, how the boundaries between them form, and how much magnetic stress gets locked into the structure instead of relaxing away. An anti-joy region is an engine assembled with its parts under tension, and the tension is not the only thing wrong with this engine. the magnetograms show at least 3 other features, each of which would, on its own, be enough to put a region on the watch list. The first is the deltas. Sunspot groups are classified by their magnetic architecture, using a scheme developed at Mount Wilson that reads like an escalation ladder. An alpha region is a single dominant polarity, the simplest case. A beta region is a clean pair, north and south politely separated, which is how most groups live and die. Add the gamma designation, and the polarities are mixed, interleaved instead of divided. And at the top of the ladder sits the label added to the scheme in the 1960s, precisely because the original categories could not capture the worst cases, the delta configuration, which means umbra, the dark cause of spots, with opposite magnetic polarity crammed together inside a single shared penumbra. Picture the north and south poles of 2 magnets forced into the same footprint, unable to separate, grinding against each other as the plasma around them churns. Delta regions are rare, and they are responsible for the overwhelming majority of the Sun's most powerful flares. The delta is, by a wide margin, the single strongest statistical predictor of major eruptions that solar physics possesses. Region 4493, at less than 2 days old, had already developed multiple delta or near-delta cores. Observers tracking the region counted several distinct areas of this kind, with the strongest sitting near the centre of the group, and it was that central delta that produced both the M2 and the M2.5. When those small C-class flares popped off from several different locations early on, that was the tell. Not one engine inside this region, several. The second feature is the sigmoids. In the extreme ultraviolet images that show the corona, the million-degree atmosphere above the surface, the magnetic loops over this region trace out S-shaped structures, and observers counted 3 of them. A sigmoid is what a magnetic field looks like when it is twisted and sheared rather than relaxed, an S drawn in glowing plasma, where a calm region would show simple arcs. Decades of observation have established sigmoids as one of the most reliable visual warnings of eruptive potential. Regions that display them erupt significantly more often than regions that do not. 3 of them, above a region still under construction, is a loaded configuration. The third feature might be the most unsettling of all, because you can watch it move. One of the region's negative polarity cores is rotating. Frame-by-frame animations show the spot turning counterclockwise in place, hour over hour like a slow gear. A rotating sunspot is a winch. As it turns, it drags the magnetic field lines anchored in it around with it, winding twist into the loops overhead the way you wind a rubber band on a toy airplane, storing energy turn by turn into a structure that is already sheared, already tangled, already holding multiple deltas and an anti-joy tilt. Rotating spots have been documented feeding the build-up to major flares again and again. The energy being stored has to go somewhere, eventually, and magnetic fields have essentially one way of letting it go all at once. Step back and assemble the picture, because this is the machine, complete, as it stands at recording time. A region that surfaced in under 2 days, against the Sun's own tilt law, with multiple opposite polarity cores grinding inside shared boundaries, S-shaped stress signatures stacked overhead, a rotating core winding in more energy, and new magnetic flux still arriving from below. Any one of those, alone, earns a watch. All of them, together, in a region under construction at the centre of the Earth-facing disk, is why the observing community treated this weekend the way seismologists would treat a new fault opening under a city. If you have watched this channel for a while, you have seen what the finished version of this kind of machine can do. Earlier this month, in our video on the Double Delta Sunspot event, we covered 2 mature delta regions that fired an X-class flare and threw a halo of solar material directly at this planet, lighting up auroras and radio blackouts around the Independence Day holiday. That is the track record of the Delta class. But notice the difference in what you are watching now. That story was about machines we met fully built, already erupting. This story is about the assembly itself. We are watching the same species of engine being constructed, bolt by bolt in real time, and it has already started test firing before the construction crews have left. Here is where honesty requires a hard turn though. Everything I have described, the deltas, the sigmoids, the twist, the tilt, adds up to a region with the raw materials for something far larger than an M2.5, and yet, so far, the eruptions have been small, sharp, and strangely contained. No plasma thrown into space, no storm launched at anyone. For a machine this loaded, the output has been, frankly, muffled. That is not an accident. Something is holding this region back, something built into its own architecture, and understanding that restraint, how it works, how strong it is, and what happens on the day it fails, is the single most important piece of this entire story. Part 5. The First Eruptions. Let us replay Monday from the Sun's point of view, because the sequence of eruptions tells a story of its own, and the pattern hiding inside it is the reason the second half of this video exists. It began with static. Small, impulsive C-class flares, quick spikes of X-ray energy, started registering from the new region through the day. Individually, they were nothing, background chatter from an active sun. What made observers sit forward was where they were coming from. Careful inspection of the extreme ultraviolet imagery showed the little flares originating from several different locations within the region, from what appeared to be a few separate delta areas. In other words, the multiple engines we identified in the last part were not theoretical. Each one was sparking independently. A single new Sunspot group was behaving like a small city of flare sites, each with its own stressed boundary between opposite polarities, each capable of snapping on its own schedule. Then the central engine spoke. An M2 flare erupted from the delta at the middle of the region, the strongest event of the group's young life to that point. And within hours it was surpassed, at 1436 Universal Time, by the M2.5, again traced to that same central delta. Two moderate flares from the same stressed core inside the region's first full day of numbered existence, while the official forecast for M-class activity still read slight chance. Now, on the sunlit side of Earth, those flares were not abstractions. Here is what a moderate flare physically does to this planet, and it does this every time. The X-ray pulse arrives with the light itself, 8 minutes and 20 seconds after leaving the sun, no warning possible even in principle, because nothing outruns light. When it strikes the upper atmosphere, it ionizes the D layer, the lowest tier of the electrically charged region called the ionosphere, 60 miles and more above your head. High-frequency radio, the band that airlines crossing oceans, ships far from shore, and emergency operators lean on precisely where no cell tower or fiber line reaches, works by bouncing signals off the ionosphere's upper layers. A flare-thickened D layer stops absorbing lightly and starts absorbing hard, and the bounce gets eaten on the way up. During the M2.5, that absorption reached what forecasters classify as 1, a minor radio blackout degrading those signals across the daylight hemisphere. Minor and brief, and it recovered within the hour, which is typical, because the D layer's extra ionization decays within tens of minutes of the X-ray shutting off, the atmosphere healing itself almost as fast as it was wounded. The blackout scale runs from R1 to R5, and for calibration, the top of that scale, driven by the greatest X-class flares, can erase high-frequency communication across the entire sunlit half of the planet for hours. Monday's event sat at the bottom rung, but the bottom rung and the top rung are rungs of the same ladder, climbed by the same region type, and the region that delivered Monday's R1 is the type in question. But understand it for what it was. A brand new object, 2 days old, 93 million miles away, reached across the solar system and briefly rearranged a layer of Earth's atmosphere. That is not a metaphor, that is a measurement. And every additional flare this region fires, as viral commentary correctly noted within hours of the event, pumps the dayside ionosphere again, one more channel of solar influence stacking onto the ones already inbound. After the M2.5, the region settled. X-ray output relaxed to roughly the C1 level and idled there. The proton monitors, watching for the energetic particle storms that big eruptions can accelerate, stayed flat below every threshold. Nothing in the radiation environment moved, and that brings us to the strangest, most important observation of the entire day, the dog that did not bark. No coronal mass ejection. Forecasters searched the coronagraph imagery for an Earth-directed eruption of solar material connected to the flare, and found nothing. To appreciate why that is surprising, and what it whispers about this region's architecture, you need the distinction between the two kinds of solar violence, because the rest of this story turns on it. A solar flare is radiation, light across the spectrum from radio to X-rays, released when magnetic field lines low over an active region snap into a new arrangement. It travels at light speed, hits in minutes, affects radio and the upper atmosphere, and is over quickly. A coronal mass ejection is matter. 1 billion tons or more of magnetized plasma physically hurled off the sun, crossing the distance to Earth over 1 to 3 days, and when one of those connects, it does not tickle the radio bands. It drives the geomagnetic storms, the auroras spilling toward the equator, the induced currents in power grids, the satellite drag, everything this channel's viewers know as the real weather in space weather. Flares and ejections often travel together. The big eruptions typically produce both, the flash and the thrown mass. Which is exactly why an M-class flare with no ejection at all is a data point worth interrogating. Part of the answer is in the flare's temporal shape. The M2.5 was impulsive, a fast, sharp spike that rose and collapsed in minutes, rather than a long-duration event that burns for an hour. This is one of the most useful rules of thumb in flare forecasting. Long-sustained flares are the signature of the field tearing open on the grand scale, the kind of restructuring that lofts a mass ejection outward. Short, impulsive flares are the signature of energy release that stays local, a snap contained low in the region, field rearranging underneath a lid that holds. One analysis of Monday's events noted precisely this, that the M flare came and went as a sharp impulse, that no material escaped, and that the eruption seemed to have happened inside something, as if the explosion had been muffled, as if the region were flaring into a closed container. Hold on to that image, the muffled explosion, because it is the pivot on which this entire story turns, and notice what it does and does not tell you. It does not tell you the region is weak. The region demonstrably has multiple stressed engines, and the energy audit, which we'll get to, says the fuel on board is already in the top class. What it tells you is that the energy being released so far is not getting out. 2 moderate flares, a swarm of small ones, and not 1 gram of solar material thrown into space. For Earth, in the short term, that is the best possible version of this region. Radio flickers instead of geomagnetic storms, but a container that muffles explosions is only good news while the container holds. And the container around region 4493 is not made of anything solid. It is made of magnetic field, the region's own outer field, arched overhead like a roof. It has a strength that can be estimated, a structure that can be mapped, and a breaking point that can be reached. The people who study this region most closely have already mapped that roof. What they found up there, the shape of it, the anchoring of it, and the specific ways it could fail, is the closest thing this story has to a fuse. Let us go look at the cage. Part 6. The cage. Above every active region on the Sun, invisible in ordinary light but traceable in the extreme ultraviolet, stands an architecture of magnetic loops. Think of it as the region's superstructure. Arches of field connecting the group's opposite polarities, layered from short, low loops near the surface, up through progressively taller and broader ones, the whole assembly rooted in the spots below like a suspension bridge rooted in its towers. The character of that superstructure, more than the size of the spots, more than the count of the flares, decides what an active region can actually do to us. And the superstructure over region 4493 has a very particular character. It is, in the language of the analysts studying it, caged. Here is what the caging means, mechanically. Down low, close to the surface, this region is a chaos of stressed, twisted, opposite polarity field. The deltas, the sigmoids, the sheared boundaries we have catalogued, each one an instability waiting for permission. But overhead, the region's outermost field, the broad loops connecting the main body of the group across the whole structure, form a canopy of comparatively orderly, strapping field lines lying across the top of everything beneath. The analysts who mapped this topology concluded that most, if not all, of the intermediate instabilities in the region are locked down under those overlying loops, held in place by the connection arching over them. The chaos is real, and the lid over the chaos is also real. The region is a pressure cooker that came with its own roof. This is not an exotic or improvised idea. The tug-of-war between eruption and restraint is one of the central problems of modern solar physics, and it explains one of the field's oldest puzzles, why some enormously energetic flares stay confined while much smaller regions manage to throw material into space. Physicists model the escape as a fight between the outward push of a twisted core trying to erupt and the tension of the overlying field holding it down, and the outcome depends less on raw power than on how quickly that overlying field weakens with height. Where the canopy stays strong, even violent energy release stays trapped underneath, producing exactly what we saw on Monday, sharp, impulsive flares with nothing escaping. Confined flares in a caged region. The muffled explosions from the last part were not a mystery after all. They were the cage, working. The cleanest demonstration the modern era offers of how much a cage can hold came in October of 2014, and it is worth knowing because it is the counterweight to every scary precedent in this video. That month, the largest sunspot region in nearly a quarter century rotated across the disk, a monster sprawling wider than 24 Earths, so large it was visible to properly protected naked eyes at sunset. It fired 6 X-class flares in less than 2 weeks, an output that should have come with a barrage of Earth-directed eruptions and severe geomagnetic storms. It threw essentially nothing. Flare after flare, some of the most energetic of the entire cycle, and the chronographs stayed quiet, because the giant's own overlying field was strong enough to slam the door on every attempt. Researchers studying that region afterward made it a type specimen of confinement, proof that even X-class energy release can stay bottled when the canopy is stout enough. The lesson cuts both ways for this week. A caged region can be spectacularly loud and still harmless beyond the radio bands, and the difference between that outcome and a hurled billion tons rests entirely on the architecture of a roof nobody can measure directly. You can even see the fingerprints of the struggle. Analysts watching the region noted that its filaments, the ropes of dense plasma suspended in the low field, stayed put through the flaring, held, in one description, by a weak but sufficient cage, at least against impulsive events of the size seen so far. Every flare this region has produced has been a test of that roof. Every test so far the roof has passed. So the question you should be asking, the question the entire observing community is asking, is what it would take for the roof to fail. And there the analysis turns genuinely sobering, for 3 reasons. First, the load on the cage is still increasing. Recall from earlier in this video that flux emergence has not stopped, that the rotating core is still winding twist into the field, that the region is still gaining complexity hour over hour. A cage under static load can hold indefinitely. This cage is under a load that grows. Second, the cage's strength is not constant either, and the same processes loading it from below can eat it from above. Continued emergence does not just add energy to the core. New flux surfacing at the edges of the region, around the leading or trailing spots, can reconnect with the overlying canopy and progressively erode it, the way a rising tide undermines a seawall, grain by grain, without any single dramatic event. The analysts watching this region flagged exactly that possibility as the thing to watch, emergence around the periphery that starts trimming away the strapping field. There is also a developing boundary at region center, where negative polarity is being driven against positive along a lengthening line of confrontation, the kind of feature physicists call a polarity inversion line, which in mature eruptive regions becomes the launch rail for the big events. The middle of this region is building one now while you watch this. Third, and this is the number that reframes everything, the energy audit. Independent analyses of the region's magnetic complexity concluded that 4493 already possesses the magnetic energy density for an X-class flare, the top classification, the class of events this channel covered when a mature double delta region fired at Earth around the start of this month. One assessment put the region's stored energy in the range of the big regions from roughly 3 weeks ago, the ones behind that Independence Day activity. Read that carefully and notice what it does not say. It does not say an X-class flare is coming. It says the fuel for one is already on board, 2 days into this region's existence, with delivery of new fuel continuing. The same analysis judged that a full breakout would probably require the whole region to activate at once rather than one delta snapping alone. The engines firing separately give you M-class impulses under a holding roof. The engines firing together is the scenario the cage has not yet been tested against, and that is the honest, unnerving place the data leaves us. Nobody can tell you the cage's breaking point, because measuring the exact strength of an overlying field from magnetograms is an inference, not a reading, and the load beneath it changes by the hour. What the observing community can do, and is doing right now around the clock, is watch the erosion indicators. More emergence at the edges, the central inversion line lengthening and shearing, the flares trending from impulsive towards sustained, the signature of energy starting to tear through rather than snap beneath. Each of those would be the sound of the roof timbers starting to creak over a room, where the fuel for a top-tier event is already stacked and still arriving, at the center of the Earth-facing disk. But suppose the cage does fail. Suppose the whole region activates, and the canopy tears open, and 1 billion tons of magnetized plasma comes off the Sun at last. Even then, this particular eruption, from this particular region, in this particular week, would face something almost no other eruption of this solar cycle has had to face. Because the corridor of space between region 4493 and planet Earth is not empty right now. Something enormous is already moving through it, and to understand what would happen when a brand new storm gets thrown into the path of one already arriving, we have to bring in the other half of this story, the one that was on the calendar before this region existed. Part 7. The Blind Spot. Before we bring in the second half of this story, we need to sit with an uncomfortable institutional fact, because it is going to shape everything about how the next week unfolds, and because it is the part of this story most likely to be twisted into something it is not. The fact is this. On the morning of July 20th, the official probability of an M-class flare was listed as a slight chance. By mid-afternoon, an M2.5 had already happened. The forecast was not shaded a little low. It was overtaken by events within hours of being issued, by a region that had not existed when the week began. The question practically asks itself, how does that happen? How, in an era when we can photograph the birth of individual sunspots in high definition, does the official outlook miss the day's main event by an entire flare class? And the answer is not incompetence, and it is not concealment. The answer is a hard physical boundary on what solar forecasting can be, and once you see that boundary clearly, the events of this weekend stop looking like a failure of the system and start looking like a demonstration of exactly where the system ends. Solar flare forecasting as practiced today is essentially actuarial. Forecasters look at the regions currently on the disk, classify their magnetic architecture, that alphabet of configurations we walked through earlier, and consult the deep statistical record of how regions with each architecture have behaved historically. A simple bipolar region historically produces almost no major flares, so its forecast probability is small. A large delta-bearing complex historically produces them at meaningful rates, so its probability is high. This works, and it works well for the Sun that exists at the moment the forecast is written. On Monday morning, the Sun that existed on paper was 3 modest-numbered regions, largely inactive, plus one new patch in the east noted as still growing, too young for its architecture to have declared itself, too new for any statistical track record to apply. The forecast described that Sun accurately. The problem is that by afternoon, a different Sun existed. This is the structural weakness of the entire enterprise, and it is worth stating plainly. Flare forecasting is a forecast of known regions. It has no mechanism, none, for pricing in a region that has not yet surfaced, for the same reason we cover down in the machinery section. The flux ropes are invisible until they breach. Helioseismology can hear the largest far-side regions through the body of the Sun, which protects us from being ambushed by a monster carried around the limb by rotation, and research techniques have occasionally caught the acoustic shadow of a big rope in the final several hours of its rise. Spacecraft stationed off the Sun-Earth line extend our eyes partway around the star, and combined with the acoustic far-side maps, they have largely ended the era of total surprise from regions riding into view around the eastern limb, the ambush that repeatedly caught earlier generations of forecasters. But a rope ascending under a blank patch of near-side surface, hours from breakout, is beneath every operational detection threshold we have. The first data point anyone gets is the emergence itself, which means the first day of a fast-emerging region's life is lived, forecast-wise, in arrears. The bulletins chase it, classification lags it, probabilities get revised after the region has already demonstrated what it can do. Monday was a textbook page from that book. The M2.5 was not unforecast because someone failed. It was unforecast because the information required to forecast it did not exist anywhere in the solar system until the region itself supplied it, at which point it was not a forecast anymore. It was news. Now, this deserves to be said with equal clarity, because the point cuts both ways. The system did not miss the flare. Detection worked perfectly. The GOES satellites clocked the X-ray spike to the minute. The blackout maps went up in real time. Magnetograms of the new region were public within the hour, and the worldwide community of professional and amateur analysts whose work this video has drawn on throughout, was dissecting the region's architecture the same day. Everything downstream of emergence ran exactly as designed. The blind spot is real, but it is a blind spot for prophecy, not for observation. We could not know in advance. We knew essentially instantly. Understanding that distinction tells you how to consume everything you will hear about this region in the coming days, and frankly, how to consume this video. When forecasters publish flare probabilities for 4493 tonight and tomorrow, those numbers now incorporate a day of demonstrated behavior, multiple M flares, the multi-delta architecture, and they will be meaningfully better than Monday morning's numbers. But they will still be actuarial statements about a region whose defining trait is that it changes faster than the paperwork. A region still under construction does not have a stable architecture to classify. Its file photo is always out of date. So treat every probability you hear this week, including any I have quoted, as a snapshot of a moving object, reliable in direction, unreliable in detail, with a shelf life measured in hours. That is not a criticism of the science. That is the science, honestly labelled. And there is one more layer to the blind spot, the one that turns it from a professional inconvenience into something worth losing a little sleep over. Everything we have discussed assumes the question is when and whether this region flares bigger. But the consequential question for Earth is whether it eventually erupts, whether the cage fails and mass gets thrown, and eruption forecasting is younger and harder than flare forecasting by a wide margin. The state-of-the-art can identify a loaded gun with real skill, the deltas, the sigmoids, the shear, all the features this region collected in its first 2 days. What it cannot do with any reliability is name the day. Confined versus eruptive, this week versus never, the field genuinely cannot say. The honest scientific position on region 4493 is a sentence that should sound familiar by now, because it has been the refrain of this entire video. We can see everything, and we can promise nothing. So here is where we stand at the midpoint of this story. A machine assembled in 2 days at the center of the Earth-facing disk. Multiple engines proven in test fires, fuel on board already sufficient for the top flare class, with deliveries continuing, a cage holding it all down, under a growing load, with known erosion mechanisms actively in play, and a forecasting system that, by its own honest accounting, will find out the cage has failed at the same moment the rest of us do, 8 minutes and 20 seconds after the fact. If that were the whole situation, it would already be worth this video. It is not the whole situation. Because while all of this was being built, something else, something completely unrelated to region 4493, was already crossing the space between the Sun and this planet on a schedule published days ago. 2 solar phenomena, born separately, driven by different physics, are now converging on the same week, the same corridor, and the same magnetic field. Ours. The first of them arrives, according to the forecast, within about 24 hours of the moment I am recording this sentence. It is time to talk about the whole. Part 8. The door that was already open. 2 days ago on this channel we told you about a hole in the Sun. If you saw that video, you know the scale of the thing. A dark opening in the solar atmosphere long enough to swallow dozens of Earths laid end to end, sprawling across both solar hemispheres, one of the giants of this stage of the solar cycle. If you did not see it, the one-paragraph version is this. A coronal hole is not a hole in the Sun itself, but a region where the Sun's magnetic field, instead of looping back down to the surface, opens outward into space and does not close. Through that open door, the Sun's outer atmosphere pours away freely, a wind of charged particles escaping at 500 to 800 kilometers per second, roughly double the speed of the ordinary solar wind around it. In the ultraviolet images, the region looks black, not because anything is missing, but because the escaping gas is thinner and cooler than the trapped glowing atmosphere around it. It is a permanent exhaust jet carved into the star, aimed wherever the Sun's rotation points it. 2 properties of these structures matter for this week, and both come from their endurance. First, coronal holes are long-lived. A sunspot region lives weeks. A large coronal hole can persist for months, surviving rotation after rotation, and because the Sun turns once every 27 days as seen from Earth, a persistent hole becomes a metronome, sweeping its stream across our planet again and again on a 27-day beat. The recurrent storms that mystified early geophysicists a century ago, disturbances that returned like clockwork with no visible spot to blame, were finally explained when X-ray telescopes in the 1970s revealed these dark openings for the first time, a story we told properly in the video 2 days ago. Second, that recurrence gives forecasters their one genuine scheduling advantage in all of space weather. A hole that storms us this week is odds-on to return in late August wearing a similar face. Sunspot's ambush. Holes make appointments. And this week, rotation pointed it at us. The hole has now crossed the centre of the solar disk, which for an open field structure is the moment of maximum consequence, because the wind it emits travels radially outward, and a hole at disk centre is a nozzle aimed at Earth. The stream takes 2 to 3 days to cover the distance, which is why the forecast reads the way it reads. Government forecasters expect the leading edge of the disturbance to reach Earth late on July 21st, with conditions escalating through July 22nd, when a minor geomagnetic storm category G1 is considered likely. The planetary K-index, the standard 0 to 9 measure of how disturbed Earth's magnetic field is forecast to reach 5, with some guidance suggesting a fraction above. KP5 is precisely the storm threshold. This is not a speculative watch. This is a scheduled arrival, published in advance, of a structure whose behaviour forecasters understand well, and it was on the calendar before Region 4493 existed. It is worth 30 seconds on why a stream of wind causes a storm at all, because the mechanism matters for what comes later in this story. The damage is not done by the fast wind alone. It is done by the collision between the fast wind and the slow wind ahead of it. Picture highway traffic. The slow, ordinary wind left the sun first and ambles outward at 300 to 400 kilometers per second. The coronal hole stream leaves later but moves nearly twice as fast, and it cannot swerve, so it ploughs into the back of the slow traffic, and at the boundary a compression zone forms, a pileup of squeezed plasma and concentrated magnetic field that physicists call a co-rotating interaction region, spiralling through the solar system ahead of the stream like a snowplow blade. That compressed boundary is what strikes first, and it is usually the most turbulent, most magnetically intense part of the whole encounter. When the forecast says late July 21st, it is the snowplow blade it expects first, with the long river of fast wind behind it, carrying the disturbance through the 22nd and beyond. The wind itself, for the record, is one of the younger facts in astronomy. The proposal that the sun continuously sheds a supersonic flow of particles was published only in 1958, was widely disbelieved by the field's leading figures, and was confirmed within 4 years when the earliest interplanetary probes flew through the flow and measured it directly. Every satellite operator now budgeting fuel against this week's stream is working inside a piece of physics younger than the interstate highway system. Whether the blade and the stream actually ignite a storm at Earth comes down to a parameter this channel has explained before and will keep explaining, because it is the single most important variable in all of space weather. The orientation of the magnetic field inside the arriving flow, the component scientists call BZ. Earth's magnetic shield points northward on the side facing the sun. If the arriving field also points north, the two fields close ranks and the stream largely slides around us, a storm that fizzles. If the arriving field points south, it links directly into Earth's field, opens a channel, and pours the stream's energy into our magnetosphere. Inside a co-rotating interaction region, the field direction is chaotic, flipping between north and south for hours at a time, which is why coronal hole storms are simultaneously so predictable in their arrival and so unpredictable in their punch. Forecasters can tell you the day the stream arrives to within hours, days in advance. What nobody can tell you until roughly an hour before it happens is which way its field is pointing, because the only direct measurement comes from Sentinel spacecraft parked 1 million miles upstream, and at 700 kilometers per second, 1 million miles is under an hour of warning. Sound familiar? It is the same shape of problem as the Sunspot blind spot, compressed from days to minutes. We know the storm is coming. We find out what kind of storm it is when it is practically at the door. Now let me place the two halves of this story side by side, because this is the point where they stop being separate stories, and everything in the back half of this video flows from the geography I am about to describe. The coronal hole is not somewhere else on the sun, unrelated to our new Sunspot machine. Look at the disk imagery from this week and you will see them together. Region 4493 sits immediately to the east of the coronal hole, close enough that observers tracking the sunspot's growth kept remarking on the neighbourhood, close enough that as the sun rotates, the new region is following the hole across the disk, a few days behind it, tracing the same path through the Earth-facing zone. The hole has crossed disk centre, and its stream is inbound. The sunspot complex is approaching disk centre with its cage rattling. One structure has already fired its shot, the other is loading. Think about what that adjacency means for the week ahead, and be careful with it, because it means two different things and they pull in opposite directions. The first meaning is for Earth. Our planet is about to spend several days inside a disturbed, compressed, fast-moving flow, with the magnetosphere wrung by the interaction region and then bathed in the stream. That is the G1 forecast, and on its own it is routine, but it means any additional solar event during this window, any eruption from the newly built region next door, would not arrive at a calm, quiet planet. It would stack on top of a system already being driven. Geomagnetic activity is not polite. It compounds. The second meaning is for the eruption itself, and this one is stranger, and it cuts the other way. Because if the cage over 4493 fails in the next few days, whatever the region throws toward Earth would have to travel through the very stream the coronal hole is pouring into that corridor right now. A coronal mass ejection launched into a river of wind moving 700 kilometers per second is not crossing empty space. It is merging into traffic, and what happens in that merge, whether the river blunts the eruption or carries it, whether the stream is our shield this week or our amplifier, turns out to be one of the genuinely unsettled questions in space weather science, with real historical examples pointing in both directions. That collision physics deserves its own part because it is the hinge on which the next several days swing. Let us run the scenarios. Part 9. The collision course. Scenario planning is what you do when the future is genuinely open, and the future of the next 5 days is genuinely open. So let us do what the professionals do. Let us take what is measured, the caged region, the inbound stream, the geometry between them, and run the branches honestly, from the boring to the historic, assigning each one the weight the evidence supports. Branch 1, and to be clear, the most likely single outcome, the cage holds. Region 4493 keeps flaring impulsively. M-class events crackle off the deltas over the coming days. Radio operators on the dayside grumble. Aurora photographers get their show from the coronal hole stream on schedule, and the two phenomena pass through the week side by side without ever combining. The G1 storm arrives late July 21st into the 22nd, runs its course as forecast, and eases as the stream wanes. In this branch, the story you're watching tonight resolves into 2 routine entries in the space weather logs, and the only thing extraordinary about the week was the construction footage. Do not mistake most likely for guaranteed, but do hold on to this branch. It is the sane baseline against which everything else should be measured. A note on the odds behind that baseline because they are not hand-waving. Even for confirmed delta regions, the historical statistics give X-class flares on any particular day something like 1 chance in several, not a coin flip, and most delta regions never fire one at all. The official probabilities issued after Monday's activity will land well below the viral certainty, and history says the official numbers are the better bet. Statistically, the most common fate of even a scary region is anticlimax. Branch 2. The cage fails, and the stream saves us. Suppose the region does what the analysts consider possible, activates broadly, tears through its canopy, and launches a coronal mass ejection during its Earth-facing window. Even then, remember what the ejection has to do. It has to cross 93 million miles of space that is currently occupied by a river of fast wind. If the eruption is modest, that river is a genuine obstacle. A slow ejection launched into a fast stream gets shoved from behind or dispersed, its internal magnetic structure worn down by the surrounding flow. An analyst looking at this specific configuration made the point directly that given how strong the stream is, it would take a high-end ejection to punch through cleanly and hold together. In this branch, the coronal hole, the thing bringing us the storm, ironically doubles as our bodyguard, and a cage failure that would have made headlines in a quiet month arrives at Earth as a smeared, weakened, glancing blow. The sun fires, and its own wind fouls the shot. Branch 3 is the one that earns this video its title, and it is not science fiction. It is a documented pattern from the history of major storms. The cage fails with force. The whole region activation the energy audit says is possible, and the resulting ejection is fast and massive enough to treat the stream not as an obstacle, but as pavement. Here is the mechanism, and it is worth understanding precisely because it sounds backwards. The single biggest brake on a coronal mass ejection crossing to Earth is the drag of the ordinary, slow solar wind it must plough through, and a big ejection loses speed to that drag the whole way, often arriving dramatically slower than it launched. But a corridor that has just been swept by a coronal hole stream is not ordinary wind. It is thinner in places, faster everywhere, pre-stirred and pre-compressed, and an ejection riding into it keeps more of its launch speed. Worse, the arrival then stacks. The interaction region has already rattled the magnetosphere, the stream is already delivering hours of fluctuating field, and into that agitated system slams the ejection with its own magnetic payload. If its field happens to arrive tilted southward, into the open channel orientation, the storm compounds far beyond what either event could have driven alone. The great storms of the historical record repeatedly show this signature, an opening act clearing and conditioning the road so the main event arrives harder, and the largest event of the last two solar cycles, the storm that lit auroras across the world in May of 2024, was driven by exactly this kind of pile-up, eruption stacking on eruption in a conditioned corridor. Branch 3 does not require any of the physics to misbehave, it only requires timing. Between those branches sits the fulcrum, and the fulcrum is time. The stream's window at Earth is roughly the next 3 to 4 days. The region's Earth-facing window is roughly the next week, as rotation carries it from 13 degrees east of centre, across the middle of the disk and toward the western limb. Viral commentary, circulating within hours of Monday's flares, gave that corridor a name that is vivid, unscientific, and geometrically accurate, the Earth Bullseye Zone, and declared that the region was displaying hyperactivity and was likely to explode with multiple powerful M-class and even X-class flares as it crossed, with the chances of solar storms launching outward over the next few days greatly increased. Let me be precise about how to weigh that. It is a commentator's read, not an official forecast, and it runs hotter than any probability the government has issued. But its logic is not wrong. It is the same logic the sober analyses point to. The energy is present. The complexity is present. The geometry for the coming week is the worst available. Where the sober analyses differ from the viral framing is only in the verb. Likely to explode is a claim nobody can support. Positioned to matter if it explodes is what the data actually says, and honestly that is unsettling enough. Because run the overlap yourself. For the next several days, and only these several days, every ingredient of Branch 3 exists simultaneously. A stream at Earth, conditioning the corridor. A loaded, still-growing, cage-tested region crossing the aim point. A declining phase sun with a documented taste for late haymakers, which we will get to. After this window closes, the ingredients separate. The stream will wane by midweek as the hole rotates on. The region will foreshorten toward the limb and, by early August, be aiming its violence at empty space beyond the sun's western edge. This is not a permanent new threat. It is a window, with edges you can almost mark on a calendar, and we are inside it as of the moment you are watching this. There is one more asymmetry to flag before we move from scenarios to consequences, because it decides how much warning you would actually get in each branch. If the cage fails, the flare's light reaches us in 8 minutes, and we would know within the hour from the coronagraphs where the mass was thrown and roughly which way. An Earth-directed ejection then takes 1 to 3 days to arrive, which is real, usable warning time, enough for satellite operators, grid managers, and frankly Aurora photographers to prepare. The stream's fine structure, by contrast, gives us under an hour of certainty at the upstream monitors. So the strange truth of the week is that the catastrophic branch comes with days of notice, while the routine branch comes with minutes. Keep that inversion in mind as we ask the next question, the practical one, the one that decides whether any of this ever touches your actual life. When the shaking starts on July 22nd, at whatever intensity this week ends up delivering, what does it actually reach? What, on the ground and in orbit, feels a storm like this? Part 10. What a minor storm touches. The word minor is doing a lot of quiet work in this week's forecast, and it deserves an audit. G1 is the bottom rung of the 5-step geomagnetic storm scale, the space weather equivalent of a small craft advisory, and the natural response is to file it under nothing. Hundreds of G1 storms happen across a solar cycle, the lights stay on, planes land, Most people alive have slept through dozens of them without knowing. All true. And yet minor, in space weather, has a specific technical meaning that is narrower than the everyday word because it describes the intensity of the disturbance, not the size of the systems exposed to it. The disturbance is minor. The footprint is planetary. Every satellite, every long conductor, every radio path on Earth sits inside the same magnetosphere, and on July 22nd that entire magnetosphere is forecast to ring at KP5. So let us walk the inventory of what actually notices honestly, without inflation, because this channel's viewers already know what the top of this scale can do, and the interesting question this week is how far down the effects reach at the bottom of it. Start overhead, with the atmosphere itself, because the least famous effect of a storm is the one with the most expensive track record at exactly this intensity. When the stream's energy pours into the upper atmosphere, the thermosphere, the wispy shell where low-orbiting satellites fly, it heats and it swells, rising like bread. Air density at satellite altitudes can jump sharply, and every spacecraft up there suddenly flies through thicker soup, losing speed, losing altitude, burning margin. In February of 2022, a storm in this same minor to moderate class caught a freshly launched batch of Starlink satellites at their lowest, most vulnerable deployment altitude, and the swollen atmosphere dragged roughly 40 of them back down to burn before they ever reached working orbit. That was not the storm of the century. That was a storm like the one on this week's calendar, meeting hardware at the wrong moment. The post-mortem numbers made the mechanism explicit. Atmospheric density along the deployment orbit had risen by roughly half again over quiet conditions. Drag spiked accordingly, and satellites commanded into a protective low-drag posture still could not climb away before the air claimed them. Density at orbital altitude is the storm's quietest weapon, invisible, unphotogenic, and billed later. The orbital economy has only grown more crowded since, and drag management during even minor storms is now a routine, unglamorous, very real line item for every operator in low Earth orbit. Come down to the ground, and the story is about conductors. A shifting magnetic field induces currents in any long conductor beneath it. Power lines, pipelines, rails, and at G1 those geomagnetically induced currents are expected to produce weak fluctuations in power grids at higher latitudes, measurable, managed, and routine. We are not going to reteach the transformer physics here. We did that earlier this month in our video on the power grid's fragile decades, made in the aftermath of that Independence Day activity. And if you want to understand why grid engineers take the top of this scale as seriously as hurricanes, that video is the place to go. The grid is only the most famous conductor. Pipelines feel the same induced currents, which interfere with the electrical systems that protect buried steel from corrosion, and operators in high-latitude regions routinely schedule around geomagnetic activity for exactly that reason. Railway networks have their own file of storm stories. Signaling systems in northern Europe and Russia have logged anomalies during strong storms, signals flickering to wrong states as induced currents leaked into track circuits. None of that happens at G1. All of it lives on the same dial this week's storm will nudge. For this week, the honest statement is that G1 grid effects are a non-event for your wall outlet, and simultaneously a real data point for the engineers whose job is to notice that the same mechanism scales. Every minor storm is, among other things, a low-amplitude rehearsal of the big one, run on the actual grid. Then there is the effect everyone can see, and this is the part of the week I genuinely want you to catch if your latitude cooperates. The Aurora. KP5 pushes the auroral oval off the pole and down toward the mid-latitudes, and the forecast geography for this storm puts the possible viewing line across the northern tier of the United States, along the latitude of Seattle, across Edinburgh and southern Scandinavia, and, in the southern hemisphere, out to Hobart in Tasmania. Now the fine print, and in July it is decisive fine print. The northern hemisphere is deep in summer, nights are short and never fully dark at exactly the latitudes the oval will reach, and twilight will wash out all but the strongest displays. Northern viewers should try, aim a camera north around local midnight on the nights of July 21st and 22nd. A long exposure will see colour your eyes cannot, but expectations should be modest. The southern hemisphere holds the good cards this time. Winter darkness, long nights, and the same expanded oval mean Tasmania, southern New Zealand, and the far southern oceans get the real show. If you are down there, this is your week. And notice what the Aurora actually is, because it reframes everything else in this inventory. That light is the visible edge of the machinery we have been describing for this entire video. The stream from the hole arrives. Its field couples into ours when the orientation tilts south. Charged particles cascade down the field lines into the upper atmosphere, and the air itself fluoresces. The colours are a chemistry lesson written at altitude. The familiar green comes from oxygen atoms struck around 60 to 150 miles up, relaxing and releasing their energy at a wavelength the human eye happens to be well tuned for. The rarer blood-red curtains come from oxygen much higher, above 150 miles, where the air is thin enough for the atoms to hold their excitation for minutes before letting the light go. Nitrogen adds fringes of blue and purple at the lower edges. Every colour is a specific atom, at a specific altitude, reporting a specific collision. When you photograph an aurora on July 22nd, you are photographing the coronal hole's exhaust, the same exhaust that region 4493's hypothetical eruption would have to swim through, striking the outermost reaches of the only magnetic shield you have. It is the entire story of this week, rendered in light, over your northern horizon. One more note on that shield, for long-time viewers, and then the inventory is complete. 3 days ago on this channel we covered the slow weakening of Earth's magnetic field itself, the growing soft spot over the South Atlantic where the shield dips low enough to matter for satellites passing through. Nothing about a G1 storm changes on that timescale, and nothing this week will be attributable to it. But it belongs in the frame for a simple reason. Every storm we have discussed tonight, every KP number, every induced current, is an interaction between what the sun sends and what the shield absorbs, and the shield is the one component of this whole system that is quietly trending in the wrong direction, decade over decade. The storms of the coming years, minor and otherwise, land on a defense that is very slowly thinning. That is the standing context behind every space weather video this channel makes, and this week sits inside it. So that is what minor touches. Satellites budgeting fuel against a swollen atmosphere, grid operators watching gauges tick, radio paths flickering on the day side every time the new region flares again, cameras pointed north from dark fields in Montana and south from beaches in Tasmania. A planet-sized system brushed at its edges, everything holding, everyone professional. That is the most likely shape of July 22nd, and if the weekend's there, it ends as a good show and a non-event exactly as forecast. But you have sat with this channel long enough to know why we cannot end the story there. Because everything in this part assumed the stream arrives alone. The entire inventory was priced for branch 1, and the reason this week is different, the reason this video is as long as it is the machine next door to the hole, the one that was not on any calendar, the one whose cage is under a growing load at the centre of the aim point. The honest way to weigh what that machine might add is not speculation, it is precedent. Because the sun has shown us, within living memory, within this channel's own archive, exactly what it looks like when a region built in 2 days decides to finish what it started. It happened in September of 2017, and the resemblance to this week is close enough to raise the hair on your arms. Part 11, September 2017. In the first week of September 2017, the sun was supposed to be going to sleep. Solar cycle 24, a famously weak cycle to begin with, was 3 years past its peak and coasting downhill toward minimum. Forecast centres were fielding questions about how quiet the coming years would be. And sitting on the Earth-facing disk was a sunspot region called Active Region 2673, a region so unremarkable that it had spent days as a single, stable, ordinary spot, the kind of feature that gets logged, numbered, and forgotten by everyone except the people paid to log it. Then, over roughly 2 days at the start of September, that region transformed. New magnetic flux began erupting through the surface around the old stable spot, at a pace that stunned the researchers who later reconstructed it. Satellites of new spots multiplying, opposite polarities surfacing crushed against each other, the whole structure reorganizing hour by hour. Analyses published afterward described it as one of the fastest flux emergence events ever recorded, with the emergence rate climbing to values with, in the words of one study, no directly comparable precedent in the modern record. The unremarkable spot became a sprawling complex of tangled deltas. The architecture went from beginner to worst case inside 48 hours. If that arc sounds familiar, it should. It is this weekend's arc. It is the same species of event we have spent this whole video documenting in region 4493, the machine assembling itself at speed, in view, from almost nothing. What happened next is why the comparison matters. On September 6th, that region fired an X 2.2 flare, and then, 3 hours later, an X 9.3, the most powerful solar flare in over a decade, the largest of the entire solar cycle, from a sun that was supposed to be winding down. Radio blackouts blanketed the day side of the planet, aviation communications degraded across oceans, and the region was not finished. Over the following days, it produced a barrage of major flares, threw a fast coronal mass ejection that reached Earth, and drove a severe geomagnetic storm with auroras deep into the mid-latitudes. And, on September 10th, as it was rotating around the western limb, fired an X 8.2 that accelerated a radiation storm intense enough to be measured on the surface of Mars. One region, built in 2 days. It went on to disrupt emergency radio communications during the very week that Hurricanes Irma and Maria were bearing down on the Caribbean, with aviation and emergency nets across the storm zone reporting hours of degraded and blacked-out high-frequency service, while rescue coordination was at its most desperate, a reminder that space weather does not check the terrestrial calendar before it acts. The September 10th event added one more distinction that belongs in this story. Its radiation storm was energetic enough that particle detectors registered it not only in Earth orbit but on the surface of another planet, where a rover's instruments recorded the dose sweeping over Mars. A structure that had been blank photosphere 2 weeks earlier ended its Earth-facing career by irradiating 2 worlds at once. Now, the discipline this channel owes you is to state clearly what this precedent proves and what it does not. It does not prove that region 4493 will do any of those things. Most rapidly emerging regions, even dramatic ones, live and die without an X-flare, and the honest baseline for this week remains the boring branch. What September 2017 proves is narrower and more important. It proves the ceiling. It proves that the specific pattern we watched this weekend, explosive emergence, compressed polarities, architecture degenerating toward complexity in real time, is the documented birth signature of cycle-defining events. It proves that the transformation can go from ordinary to historic in less time than the gap between 2 of these videos. And it proves, most pointedly, that a declining, quieting, past its peak sun retains the full authority to produce its most violent event on any given week it chooses. Nobody watching that single stable spot on September 3rd, 2017, had any inkling of what the 6th would bring. The construction phase looked to the instruments of the day like a curiosity. The curiosity was the warning, and that is the pattern with declining phase suns generally, which is worth a moment because it collides with the most natural assumption people carry about the solar cycle. The assumption is that past the peak means past the danger, that the descent to solar minimum is a long anticlimax. History does not agree. The Halloween storms of 2003, among the fiercest of the space age, arrived 2 to 3 years after cycle 23's maximum on the way down. That late October barrage blacked out a city in southern Sweden when induced currents tripped its grid, forced airlines to reroute polar flights at real fuel cost, damaged or degraded dozens of satellites including one Japanese Earth observation spacecraft lost outright, and closed with the X-ray event so strong it saturated the sensors built to measure it, its true size, estimated near X45, reconstructed afterward from the damage to the measurement itself, all of it from a sun officially in decline. The September 2017 barrage came 3 years down the slope of cycle 24, and the storm that stands above all others in the record, the Carrington event of 1859, the one that set telegraph offices sparking and painted auroras over the tropics, arrived on the declining phase of its cycle from a sun already past its peak. The declining phase thins the crowd of active regions, but the regions that do form seem to carry disproportionate menace, and the giant coronal holes of the descent, the same family as the one whose stream arrives this week, open their doors widest in exactly these years. The tale of a solar cycle is not a decrescendo. It is a quieter room in which the occasional gunshot sounds louder. Which brings us back to 2026, and to the reason this part is not merely a history lesson. Solar cycle 25 passed its maximum in 2024 into 2025. We are now in the early declining phase. The exact regime, the same downhill stretch in which 2003 and 2017 and, if the reconstructions are right, 1859 all detonated. The ingredients on the disk this week read like the setup of that pattern. A giant declining phase coronal hole, door open, stream inbound. And beside it, a region that just executed the most convincing impression of 2673's construction phase that this cycle has offered: multiple deltas, record pace emergence, first M flares inside 2 days, energy audit already at the X threshold, cage load still climbing. I want to be measured here, because measured is what this channel is for, and the difference between the 2017 precedent and this week is real and worth naming. 2673's transformation happened around an existing anchor spot, and its X flares came after the architecture had a few more days to mature than 4493 has yet had. Emergence can also simply stop. Regions stall, decay, and unravel, and the most likely week remains the one where this one underdelivers. The precedent sets the ceiling, not the forecast. But the ceiling is the point. When analysts watching this region say it is already pushing the energy levels of the big regions from 3 weeks ago, when the viral commentary calls it hyperactive and warns about its transit of the aim point, when this channel makes a video with the word erupting in the title, the ghost in the room is September 6, 2017, the day the sun demonstrated what the construction pattern we just watched can become, given one more turn of the winch. The observing community is not watching 4493 because of what it has done. An M2.5 is forgettable. They are watching because of what it is shaped like, and it is shaped like the last one, the one that waited until everyone had filed it as curiosity and then fired the biggest shot of its decade. So the precedent leaves us with the week's real question sharpened to a point. The historical record says machines like this one sometimes finish loading and sometimes fall apart, and gives us no tool to tell which is underway. The measurements say the fuel is aboard and the cage is holding today. The calendar says the aim point window closes in about a week. Put those 3 statements together, and the only honest posture left is the one the professionals have already assumed. Watch the region. Watch it hourly. Which raises a fair question you may already be asking. In a story defined by blind spots, by ropes we cannot see, and cages we cannot weigh, and field directions we learn about an hour out, what exactly are the watchers watching for? What would the beginning of the bad branch actually look like, on the instruments, in the data, hours before it became news? It turns out there is a checklist, and walking through it is the closest thing this story offers to a warning system you can follow yourself from your own screen this very week. Part 12. The Watch List. There is a checklist, and it is not secret. The professionals watching Region 4493 over the next several days will be reading a handful of specific indicators, each one public, each one updating in near real time, and each one meaningful hours before anything becomes a headline. Walking through them does 2 things for you. It hands you the tools to follow this story live instead of waiting for coverage to digest it. And it forces every vague anxiety this video may have stirred up into concrete, checkable, falsifiable form, which is the difference between being informed and being spooked. This channel is in the first business, so here is what the watchers are watching, in rough order of how early each signal arrives. The first indicator is the official magnetic classification, and it is probably the next domino to fall. Every day, forecasters publish an updated inventory of the regions on the disk, each with its magnetic label. As of the most recent bulletin available at recording time, the paperwork on 4493 still lags the imagery, which is exactly what the blind spot part of this video would predict. The file photo is always out of date. But the magnetograms already show what they show. Multiple opposite polarity cores crowding shared boundaries. Watch for the moment the official classification catches up, and the label acquires the word delta, formerly in the beta-gamma delta class. That upgrade will not mean the region changed. It will mean the paperwork admitted what you already knew from this video, and from that moment, every forecast probability attached to the region will jump, because the actuarial tables for delta regions are a different, darker book. The second indicator is the overnight flare record, both its count and, more tellingly, its shape. Flare counts you can read directly off the public X-ray flux graph, that jagged line from the GOS satellites that this community treats as a heartbeat monitor. The graph is logarithmic, with the flare classes stacked as horizontal bands, A at the bottom through B, C, M, and X. So a glance tells you the state of the star. A line idling in the B-band is a sleeping sun. A line dancing across the C-band with spikes into M is exactly what this week should look like, and a line that climbs into the X-band is a day with a name. Morum-class spikes overnight means the engines are still firing and the load is still being exercised. But the sophisticated read is the shape of each spike. Remember the distinction that has carried this whole story? Impulsive spikes are snaps beneath a holding cage. Long-duration events are the field tearing open. The single most alarming thing the X-ray record could show this week is not a bigger number. It is a wider spike. An M flare that refuses to end, that burns for an hour instead of minutes, would be the signature of energy release changing character, of the roof beginning to participate instead of contain. Flare class measures loudness. Duration measures escape. The third indicator lives in the magnetograms, and it is the slowest and most decisive the state of the cage's foundations. The analysts we have leaned on throughout flagged two specific locations. The periphery, where fresh flux surfacing around the leading or trailing spots would begin reconnecting with and eroding the overlying canopy. And the center, where that confrontation line between opposed polarities, the developing polarity inversion line, has been lengthening and shearing. Growth at either location does not produce headlines on the day it happens. It produces the conditions for the headline days later. This is the deep structure of the week, changing slowly underneath the noisy flare record, and it is where the region's real trajectory will be legible first. The fourth indicator is the one that converts everything from solar news into Earth news, the coronagraphs. The moment any large flare occurs, the question that matters to this planet is answered not by the flare's class, but by the white light imagery from the sun-watching coronagraphs in the following hour or two. No expanding cloud, and the event was confined. The cage bent but held. Earth's stake in it ends at the radio bands. An expanding cloud, and the geometry questions begin immediately. Is it a halo, meaning aimed along the Sun-Earth line? How fast? How massive? And from those answers flow the 1 to 3 day arrival forecasts, the stacking calculations against whatever remains of the stream, the entire Branch 3 machinery from earlier in this video. Flare first, coronagraph second. That two-step is the rhythm of every consequential space weather day, and it is the rhythm to expect if this week turns. And the fifth indicator is verification of the storm we already know is coming. Late July 21st, watch the solar wind speed at the upstream monitors begin to climb as the interaction region arrives. Those monitors are worth knowing by role if not by name. A small permanent guard of spacecraft holding station at the gravitational balance point 1 million miles sunward of Earth, sampling the wind that will reach us tens of minutes later, the closest thing our planet has to a tripwire. Their public readouts show speed, density, and that all-important field direction, and on the evening of the 21st the arrival will be legible in them before the first gauge on Earth moves, speed stepping upward, density spiking as the compressed blade passes, the field beginning its storm-deciding wobble between north and south. Through July 22nd, watch the KP index, the forecast says 5. If it verifies at 5, the forecast machinery is calibrated and this week's baseline is behaving. If it runs hot, if 5 becomes 6, that is worth noticing. Not because a G2 storm is dangerous, it is barely less routine than G1, but because it would mean the corridor between the Sun and Earth is carrying more punch than modelled this week, which quietly raises the price of everything in Branch 3. The baseline storm is, among its other roles, a live calibration test of the exact forecast system we would be depending on if the region next door does something worse. Notice what this checklist adds up to: classification, flare shape, foundation erosion, coronagraph verdicts, storm verification. 5 public data streams, all free, all watchable from the same devices you're using right now, together forming a running answer to the only question that matters this week: is the cage holding? That access is genuinely new in human terms. Your great-grandparents got their space weather warnings, when they got them at all, as telegraph system failing under their operators' hands. You get the same feeds the forecasters read in real time for nothing. The asymmetry of this whole story, watch everything, control nothing, at least splits its first half with everyone. A word of calibration before we leave the checklist though, because tools without calibration make people crazy. If you follow these feeds this week, you will see activity. That is a promise. You will see M flares from this region, possibly a string of them. You will see the KP gauge climb into storm range on schedule, you will quite possibly see the Delta classification land, and commentary around all of it will spike accordingly. None of that by itself is the bad branch. All of that is the expected week, the baseline, the storm that was on the calendar, and the region doing what caged regions do. The bad branch has a specific narrow signature, the long-duration event, the halo in the coronagraph, the arrival forecast with Earth in it, and if it ever appears, you will not need this channel to tell you. Every agency on the planet will say it plainly and within hours. Everything short of that signature is the sun being interesting, not the sun being dangerous. Hold that line and the feeds inform you. Lose it, and they own you. There is one more thing the checklist cannot do, and naming it honestly is the bridge to where this story has to go next. The checklist tells you what is happening. It cannot tell you what is about to happen, and by now you know that is not a software limitation. It is the physics of a star that keeps its decisions below the surface until they are made. Which means everyone on Earth, the forecasters included, is in the same posture this week. Pressed against the glass, reading gauges, waiting on an object 93 million miles away to reveal a choice it has, in some real sense, not yet made. And whenever human beings are put in that posture, watching something enormous and consequential that they cannot influence or fully predict, something else always happens, reliably, every single time. The explanations arrive, the theories, the whispers that someone, somewhere, knows more than they're saying. This week is already generating them. Let us deal with them head on. Part 13, the questions everyone is asking. Whenever the sun does something sudden, a predictable second storm follows the first one, and it happens entirely on Earth. It moves through comment sections and group chats and video feeds, and by Monday evening it was already well underway around region 4493, the theories. Some of them are reasonable questions wearing dramatic clothes. Some of them are old myths that reactivate on schedule every time our star clears its throat. This channel's standing policy is to take them seriously enough to actually examine, because dismissing a question is not the same as answering it, and because buried inside almost every viral claim about this week, there is a real kernel worth extracting. So let us take the 4 biggest ones, in ascending order of how interesting they turn out to be. The first claim is the simplest. Something is wrong with the sun, a star that builds an eruption machine in 2 days against its own tilt laws, while opening a giant hole in its atmosphere, sounds like a star malfunctioning, and versions of that sentiment were circulating widely within hours of the M flares. It is an old feeling, with a long paper trail. When the Aurora reached the tropics during the Great Storm of 1859, newspapers filled with accounts of citizens who took the red sky for distant cities burning, and telegraph operators for whom the equipment misbehaving felt like the world's new machinery being judged. Roman chroniclers 2,000 years ago logged blood-coloured night skies as portents before disasters. The instinct that a misbehaving sky means a misbehaving cosmos is possibly the single oldest recorded human reaction to space weather. The honest answer, this week as in every one of those weeks, is that every individual behaviour on display is documented, physical and precedented. Rapid emergence has a research literature. Anti-joy regions are rare, but they are a recognised, studied category of rare, with statistics. Giant declining phase coronal holes are so normal, they were the subject of their own video on this channel 2 days ago. What has actually changed is not the sun. It is the resolution at which humanity watches it. For nearly all of history, this weekend would simply not have been observed. A few new specks on a disk almost nobody examined daily. The Solar Dynamics Observatory era means every fast birth, every strange tilt, every twist now unfolds in public, in high definition, and rare but normal events observed continuously feel like abnormal events accumulating. The sun is not behaving unusually, it is being seen unusually well, and our intuitions have not caught up to our instruments. The second claim does not survive contact with arithmetic, but it returns every cycle, so let us retire it again. The idea that solar activity is being triggered or steered by secret technology, by weapons research, by spacecraft, or, in its astrological costume, by alignments of the planets. Run the energy audit. A single M-class flare releases more energy in minutes than human civilization generates in years, and an X-class event multiplies that tenfold. The combined output of every device our species has ever built amounts to a rounding error against one afternoon of one active region. As for the planets, tidal forces fall off steeply with distance, and the gravitational stress any planet exerts on the Sun is dwarfed, by orders of magnitude, by the Sun's own internal churn. Nothing humanity owns, and nothing the solar system's geometry provides, reaches the scale where the solar dynamo would notice. We are not steering this. That is rather the point of this entire video. The third claim is the one with genuine teeth, and it deserves respect. They knew, or they should have known, and the fact that no forecast warned us proves the system is either blind or lying. You have now sat through the full anatomy of Monday's forecast miss, so you already hold the answer, but notice how the claim splits under examination into one half that is false and one half that is uncomfortably true. The false half is concealment. Every byte of the data in this story, the X-ray record, the magnetograms, the stormwatch, was published in real time by the same agencies the theory accuses, and the global community analysing it, whose work this video has drawn on throughout, is not a priesthood. It is anyone with a browser. A cover-up that publishes its own evidence within minutes for free is a poor cover-up. But the true half is the blind spot itself, and the mature response to this week is not to deny that half. It is to state it more precisely than the conspiracy does. No agency on Earth can see below the photosphere. Days ahead warning of new flux does not exist at any price, at any clearance level. The system is not hiding what it knows. It is exactly as blind as it says it is, in exactly the places it says it is blind. That should not comfort you particularly. But it should redirect the unease toward its correct target, which is not institutional deceit. It is a star that offers no appointments, and the fourth claim is barely a conspiracy at all, more a mood, and it is the one this channel takes most seriously. The feeling that this is all building towards something, that a fast-grown region beside a giant hole in a declining cycle is a pattern, an omen, the setup of a story whose ending is already written. You've heard the rational version of the rebuttal threaded through this whole video. Coincidence is the default explanation for two unrelated solar phenomena sharing a week. The region and the hole are driven by different physics. Their adjacency is real, but their conspiracy is not. All true. And yet the mood is not entirely wrong, and intellectual honesty means saying so. Because there is a version of the pattern claim that is simply the science restated. We're in the declining phase of a cycle, the historical home of the largest single events. The energy audit on this region is real. The corridor conditioning is real. The window is real. Nobody serious is claiming a catastrophe is scheduled. What the sober version of the mood says is that the ingredients of a memorable week are assembled in one place, on a timer, and that claim is not a theory. It is the thesis of this video sourced. The line between paranoia and preparedness, here as everywhere, is whether the pattern you feel can survive contact with the data. This one, in its modest form, can. Which is, in the end, why this channel does these segments. Not because the theories are strong, but because the instinct beneath them, the refusal to believe that something this large is being fully and honestly described, deserves a better answer than a shrug. The better answer is the one you now have. It is being honestly described. The description is public, hourly, and precise. And the honest description is stranger and less comfortable than the conspiracies, because every theory on tonight's list at bottom offers the same secret consolation, that someone, somewhere, is in control, malicious perhaps, but in control, steering the sun, hiding the forecast, writing the ending. The data offers no such person. There is no hand on this machine. There is a star running open loop, watched by 7 billion people who found out about its newest engine the moment it surfaced, and not 1 second before. Sit with that, because it is the true shape of our situation, this week and every week, and then follow it one step further to the question the theories are all secretly avoiding, the one that remains after every myth is retired. If no one is steering, if warning tops out at hours and control tops out at nothing, then what, exactly, is our relationship to this star supposed to be? What does it mean to live, permanently, downstream of a machine like this one? That is not a debunking question. That is the question, the one this whole strange weekend has been asking underneath everything. And it deserves the final word. Part 14. Living Downstream. Every human being who has ever lived has lived downstream of the sun. That has been true since before there were human beings, before there was anything alive to notice. What is new, and it is newer than most people appreciate, is that we have become downstream in a second, sharper sense. Not just warmed by the star, but wired to it. Consider how recently the wiring happened. For roughly 300,000 years, our species' exposure to a solar eruption was, in practical terms, zero. The sky might glow strangely for a night or two, and did, over civilizations that recorded those glows as omens, armies in the air, blood over the horizon. Nothing broke, because there was nothing to break. The first generation to own technology the sun could reach was the generation of the telegraph, and the sun found their machines almost immediately. The Carrington storm arrived in 1859, barely a decade and a half into the telegraph era, as if the star had been waiting for something to answer back. Operators watched sparks jump from their equipment, and some disconnected their batteries and passed traffic on Aurora-induced current alone. That was the entire vulnerable surface of civilization in 1859. A few thousand miles of wire, and the largest storm in the record could do no more than rattle it. The near misses since then have been generous teachers, if anyone cares to enroll. In July of 2012, a coronal mass ejection of genuinely Carrington-class ferocity tore through Earth's orbit, measured directly by a solar observatory that happened to be stationed along its path, moving at speeds that would have crossed to Earth in well under a day. It missed us by about 9 days of orbital position. Had it launched a week and a half earlier, the same cloud would have struck this planet head-on, and the studies written afterward did not mince words about what a repeat of 1859 would do to the systems below. 9 days, on an orbit of 365, is not a margin. It is a coin toss we did not know we were making. Now count what we have added in the 6 generations since. Continental power grids synchronized to the millisecond, woven into every act of modern life, from water treatment to hospitals, to the payment system behind your groceries. Tens of thousands of satellites, with thousands more launching every year, carrying navigation, timing, communication, weather, and the quiet machinery of finance, all of them flying through the exact layer of atmosphere that swells when the sun exhales. Aviation routed over the poles where the shield is thinnest, high-frequency links backstopping every ocean crossing. And threaded through all of it, the dependency almost nobody names, timing. The satellite navigation constellations do far more than move blue dots on maps. Their clocks synchronize cell networks, timestamp financial trades, coordinate the switching of power across grids, and discipline the schedules of industries that have never thought of themselves as space-dependent. A storm that degrades those signals does not just inconvenience drivers. It introduces jitter into the metronome the modern economy keeps time by. A civilization that took its nervous system, which for all of history had been made of people, and rebuilt it out of precisely the 2 materials a geomagnetic storm speaks to: long conductors and orbiting electronics. None of it was designed with the sun in mind, because nearly all of it was designed inside a run of decades that happens, by pure luck, to have avoided a top-tier storm. The last unambiguous grid-scale hit of the modern era was Quebec in March of 1989. A 9-hour provincial blackout from a storm well short of Carrington class, delivered to a grid smaller and simpler than today's. Everything built since has been built on an untested assumption. Hold that thought against the events of this weekend, and the real meaning of Region 4493 comes into focus. Not this region specifically, whose most likely fate is still the boring branch, a week of M flares under a holding cage and a quiet slide around the western limb. The meaning is what its birth demonstrated, in controlled, documented public conditions. It demonstrated that the star our civilization is wired to can assemble a weapons-grade magnetic structure from nothing, in less time than a long weekend, at the aim point, and that the sum total of our species' response options, after 2 centuries of scientific revolution, after fleets of solar observatories and forests of instruments, is to watch it happen at high resolution. We have upgraded from ignorance to spectatorship. The distance from spectatorship to control is not a matter of better instruments. It is a wall built into the physics, the opacity of a star's interior, the light-speed arrival of flare energy, the scale mismatch between a civilization's entire energy budget and one afternoon of one active region. Some walls you engineer past. This one you live with. And living with it, honestly, has a shape, and it is not fear. This deserves to be said directly, because a video like this one walks a line, and you deserve to know which side of the line this channel stands on. The correct response to this weekend is not dread. Dread is for threats you can neither predict nor survive, and this is neither. Even the worst storms in the record were survivable events, hard on infrastructure, hard on the systems we lean on, recoverable by societies that had made even modest preparations. The engineers who manage grids and satellite fleets are not bystanders. Hardening is real. Forecasting inside the possible envelope is real and improving, and the difference between a bad storm meeting, a prepared system, and an unprepared one is the difference between an expensive week and a historic one. The correct response is the one this video has tried to model for its entire runtime. Attention. Precise, calibrated, unhysterical attention, of the kind that knows what the gauges mean, knows which signatures matter, and refuses both sleeps, the sleep of never looking up and the sleep of looking up and seeing only stories. Because here is the perspective that all of this finally opens onto, and it is the widest one this channel knows how to offer. The star we have spent this whole video treating as a threat is also the only reason there is anyone here to threaten. Every atom of carbon in your body was forged in a star. Every calorie you've ever burned was sunlight, briefly detained by a leaf. The same magnetic violence that builds delta regions and hurls plasma at planets also over billions of years blew away the early solar system's chaos, and the same wind that will rattle our field on July 22nd has, for 4 billion years, wrapped this solar system in a protective bubble that holds back the harder radiation of the galaxy. We live inside the sun's weather because we live inside the sun's shelter. They are the same thing. Region 4493 is not an aberration in that arrangement. It is the arrangement seen up close on a week when the machinery happened to face us. And the machinery will keep facing us, on its own schedule, forever. That is the last thing to say plainly. This week's window will close. The stream will pass, the region will rotate away, carried around the far side to grow or die where we cannot watch, and note the date, because the sun's rotation makes one promise it always keeps. Whatever survives of this region, or whatever that same restless longitude builds next, comes back around in 27 days, in mid-August, and this channel will be here when it does. But there will be another region after that, and another window, another fast berth at a bad address in some month or year nobody can name in advance. Somewhere in the sun's future, statistically certain, dated by no one, is the next September 2017 and the next Carrington. Our whole relationship with that certainty comes down to what we do between windows, the hardening, the watching, the refusal to file the quiet weeks as permanent. So, as the stream arrives and the gauges climb, here is where we leave it. The sun built something this weekend in front of all of us, faster than anyone believed comfortable, and has not finished building it. The cage is holding, the fuel is aboard, the window is open for about a week. Nothing in the data says catastrophe, and nothing in the data says relax, and living between those two sentences with clear eyes is simply what it means to be the wired species orbiting an unwired star. One question, though, stays open tonight, and it is the one to carry with you into the next few days. The analysts told us what a full breakout would require, the whole region activating at once, every delta firing together, and they told us the region has not yet shown it can do that. But this region has answered every other question ahead of schedule, existence, complexity, first eruption, all early. When the next bulletin drops, and the one after that, watch for the only line that matters, whether the engines of 4493 are still firing separately, or whether they have begun, at last, to fire together.